everyone, I'm Professor Harrison, and welcome back to our module on probability for finance. Today we're going to be covering the t-distribution, when we use it instead of the normal distribution, what degrees of freedom actually mean, and why small updates end up requiring fatter tails. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to his family fortune. He recently received a few early estimates of what the appraisal will be for his father's estate. He only has a few of these estimates, however, and he's trying to figure out what this means for the precision of what his father's estate actually ends up being worth. To figure out what these things mean, he opens up another one of those mysterious letters. Suppose you want to estimate the true mean return of a fund. You have a sample of n observations. You calculate the sample mean, and you want to build a confidence interval, a range that's likely to contain the true mean. If you knew the true population standard deviation sigma, you could use the normal distribution. The standardized quantity would be the sample mean minus the true mean divided by sigma over the square root of n, and that would follow a standard normal distribution. But you almost never know the true standard deviation of something. You have to estimate it from your sample as well. For example, when you're trying to calculate the standard deviation of a fund's returns, you don't know the true standard deviation of what actually generates those fund returns, but you can use historical data to estimate that standard deviation. And when you replace the sigma with this new standard deviation from the historical data, S, something changes. You've introduced an additional source of uncertainty. The denominator is no longer a fixed known quantity, and it's a random variable in itself, varying from sample to sample. This extra uncertainty about the true standard deviation of our variable makes it so that we can no longer use the standard normal distribution. The reason being, we suddenly have much heavier tails than the standard normal. The distribution that captures these heavier tails is the t-distribution. The t-distribution, with nu degrees of freedom, written t sub nu, arises exactly in this situation. Let's think of an example that illustrates this concept. Say you want to know the average number of hours college students sleep per night. That true average across every college student in the whole world is mu. You don't get to measure everyone, so you survey a random sample of n equals 20 students and record how long each one slept. Those 20 numbers are your sample. From those 20 observations, you compute two things. X bar is the sample mean, just the average of your students sleeping the 20 times. Say it comes out to 6.4 hours. Then we can also calculate S, the sample standard deviation, which measures how spread out those 20 values are around that average. Let's say S is equal to 1.2 hours. From your data, X bar is going to be your best estimate of how many hours per night college students sleep on average. S is going to be your best estimate of the standard deviation of that value. However, you don't know the true population values of either of these numbers. In reality, the average is likely not 6.4 hours and the standard deviation is also not 1.2 hours. If you were to draw from 20 different students, you'd almost certainly get a different value from either of these two, and if you were to end up sampling every single student, you would find the true population value, which also would likely be different. Now, what you want to ask is 6.4 hours meaningfully different from, say, the recommended 8 hours of sleep? To answer that question, you need to know how much X bar typically bounces around from sample to sample. That's the standard error, S, over the square root of n. We'll learn in a later unit exactly where this formula comes from when we handle the law of large numbers. But the key thing to notice here is that as our sample ends up increasing, our n, our number of observations, becomes larger, our standard deviation for our average will end up going down. We end up getting that the square root of 20 is about 4.47, so the standard error of our estimate is going to be 1.2 divided by that 4.47, giving about 0.27 hours. That's how much you'd expect your sample mean to vary if you ran the survey again with a fresh group of 20 students. Using this 0.27 hours, we can now figure out how many standard deviations away from the recommended value of 8 hours of sleep per night our sample ends up sitting. So we end up taking our 6.4, subtract off the 8 recommended hours of sleep per night, and divide by 0.27. We end up getting approximately negative 5.9. That's how many estimated standard errors your sample mean sits away from our target of 8 hours of sleep per night. If we knew sigma here exactly, the true population standard deviation, then this measurement would end up following a standard normal distribution. But because S itself is an estimate that varies from sample to sample, the quantity ends up slightly more spread out than normal, and that's what the t-distribution tries to account for. The t-distribution is symmetric around zero, just like the standard normal. The key difference is the tails. the t distribution has heavier tails. Extreme values are more likely than under the normal distribution. How much heavier depends on what's called the degrees of freedom, which we'll cover in a second. The degrees of freedom parameter controls how heavy the tails are here, and the intuition behind the name is worth understanding. When you estimate the sample mean from n observations, you use up 1 degree of freedom. This means you forced one constraint onto the data. Here, that constraint is that the deviations from the mean must sum to 0. That leaves n minus 1 free pieces of information to estimate the variance. So the sample variance is computed with n minus 1 in the denominator, not n. And the corresponding t distribution has n minus 1 degrees of freedom. The practical effect with this is with very few degrees of freedom, the tails are extremely heavy. At nu equals 1 degree of freedom, the t distribution is a special case called the Cauchy distribution. And the mean here doesn't even exist because the tails are so fat. At nu equals 5 degrees of freedom, the tails are noticeably heavier than normal. At nu equals 30, you're nearly indistinguishable from the standard normal distribution, and as nu approaches infinity, the t distribution becomes exactly like the standard normal. The rule of thumb most people use is that for samples of 30 or more, the t and normal distribution are going to give very similar answers. For samples smaller than 30, the t distribution matters and you should use it. Back to finance. Consider a fund with only 3 years of monthly data, 36 observations. To understand whether its mean return is genuinely positive, you use a t distribution with 35 degrees of freedom. At a 95% confidence level, the critical value from the normal distribution is 1.96, but T35 at 95% is 2.030. That's higher, meaning you need more standard deviations of evidence before you can be confident that the result isn't just sampling noise. That extra cushion is appropriate. The smaller your sample, the less certain you can be. The opposite is also true, however. If we end up getting more observations, we can become more confident about what the true nature of our distribution actually is. So for example, suppose a fund has 3 years of monthly return data, so 36 observations. Here our degrees of freedom are going to be one less than that, so 35. The t critical value at the 95th percentile with 35 degrees of freedom is 2.030. The standard normal's equivalent is going to be 1.960. Those are close, but not exactly the same with only 36 months of data. The reason being that the extra uncertainty from estimating S rather than knowing sigma, the true underlying standard deviation, pushes that threshold up. Now suppose the same fund has been running for 10 years and we get 120 months of data. Now our degrees of freedom are 119, one less than 120, and the t critical value at the 95th percentile with 119 degrees of freedom is 1.980. That's much closer to the normal distribution's equivalent of 1.960. The two distributions are basically indistinguishable at that sample size. And at 30 degrees of freedom or above, the gap between the t distribution and normal distribution is small enough that for most practical purposes it doesn't matter very much. The t distribution is essentially doing you a favor when sample sizes are small. It's saying you don't know sigma precisely, so I'm going to require a bit more evidence before you can draw conclusions. As the sample grows, and S becomes more reliable as an estimate of sigma, the true standard deviation, that requirement gradually relaxes until the t and normal distribution end up converging completely with an infinite number of observations. Danny puts down the letter. So far, only a handful of items in the estate have been formally appraised. 5 items have valuations. He's trying to estimate the total value of the estate from those 5 numbers. He's been using the sample mean of the appraisals and treating it as if he knew the true distribution of asset values with certainty. He hasn't been accounting for the fact that with 5 observations, his estimate of the spread is itself uncertain. He runs the calculation again. He has 5 observations, so the degrees of freedom is going to be 4. The t critical value at 95% with 4 degrees of freedom is 2.776. Comparing that to the normal's 1.960, his confidence interval has just gotten substantially wider. His father's estate could be worth considerably less now that he knows that he's been assuming the wrong numbers. Or potentially it could be worth considerably more. 5 appraisals are not enough to know. Over the following weeks, more items will get valued, and as each new appraisal comes in, he knows that he can recalculate and try and figure out what the true underlying nature of his father's estate looks like. But for now, with only 5 observations and 4 degrees of freedom, he knows that he can't make any serious assumptions about what the estate's future is going to look like. Instead, he'll have to wait for that degrees of freedom to go up as more observations end up coming in. So that's the t distribution and degrees of freedom. Whenever you're estimating a mean and your sample size is small, the t-distribution is the right tool. It accounts for the extra uncertainty that comes from estimating sigma alongside the mean, producing heavier tails and higher critical values. As sample size grows, the degrees of freedom increase, the tails thin out, and the distribution converges to be the standard normal. Degrees of freedom is basically a measure of how much information you have, and the distribution automatically adjusts the precision of your inference to match.